I'm Debbie from Aberdeen Science Centre, and welcome to our first STEM exchange, where we're celebrating Maths Week Scotland. We've got Irakli here from the Department of Mathematics at the University of Aberdeen. He's going to be telling us a bit more about topology. We are hoping to run more sessions like this, more STEM exchange sessions. And if you want to keep informed, please do sign up on our newsletter. My colleague India is going to pop it in the chat just now if you fancy signing up, if you're not already. And it will be on the description on the YouTube video as well. So Irakli, if you're ready, I will pass over to you and enjoy.
All right, thank you very much for the introduction and for this opportunity to give this talk. I have to admit, I'm a bit nervous because I have never given such a talk for like very general audience, you know, so I often give talks for mathematicians, but not for like non-mathematicians. So I apologize in advance if this doesn't really go up to your standard you are used to. So yeah, but let's see. So here is an introduction to topology. Let's start with discussing generally what the modern pure mathematics is doing. And I mean, it's a huge subject with many different areas. And some of these areas you might have heard names of. And let's just mention them before we really go to topology. So one of them is analysis, which is something that studies functions. And you might remember what these are from your school. Then there is algebra and number theory, which kind of studies numbers or equations. And then something which is relevant for us today is geometry and topology, which studies figures, geometric objects, distances, shapes. And now, I mean, you might think that this guy is going to keep on now writing this kind of text on the slides, but most of the time what we will be doing in this talk will be looking at pictures. So let's start looking at some pictures. So we switch now to geometry and topology. So geometric objects, examples of geometric objects. I mean, here, for example, this is this famous Möbius band, which we will discuss shortly. Here is a sphere, here is a torus. These kind of things should be familiar for many people here. Then we got here something very similar to football ball, not quite a ball because it's not round. Here is a knot. This is a Klein bottle. Again, something you might have seen in some popular science talks. And then all in all, these things are some things we can still kind of imagine, but now we start here seeing some more outrageous geometric objects. This is something called Alexander's horn sphere. That's a Calabi-Yau threefold, and that's a three-dimensional sphere. So these are things that are not quite really, I mean, these last two, not quite really sitting in three-dimensional world, but I will still mention at the end of this talk what they really are. Okay, so now looking at these objects, of course, some of them are objects from real life, like these things here, for example, we meet them, some of these things, we meet them in everyday life. Like look at this picture, for example, like football ball or donut or a knot. These things, of course, show up in everyday life. So in that sense, studying those objects here is nothing crazy. I mean, these are really things in real life, and we have to study them. Okay, so now what's the difference between geometry and topology? So as I said, this talk is about topology. So maybe we should first explain what's the difference between these two subjects. I mean, this is a very naive explanation again. Many people might argue against this reasoning, what I will do here. But anyways, geometry is something that often studies metric properties of geometric objects. So like shortest distance between points or measures or volumes. And these are kind of things like more like quantitative kind of things. That's what geometry very often studies. Whereas topology, this is concerned more about shapes of objects, you know, how they look like and what are the characteristic properties of these shapes, as opposed to how exactly large they are or what's the volume of something. So really interested in the characteristic properties of these shapes. And so this talk is on topology. So this talk is on topology, and what I want to show you is the first example of such a characteristic property, such a topological property, which you can observe on some things which is not really dependent on the size of objects. So here is the first example. This is a cylinder. You can obtain this by taking a piece of paper and gluing two sides. And we don't have a top and the bottom for the cylinder. And what the cylinder has a property is that, like, if you look at this black point in the middle of the cylinder on the circle, and you put an arrow, outward pointing arrow on this black point, when this black point is running around, imagine this black point is a bug or something that is running around along the circle. While running around the circle, this arrow will keep point outwards, and then once this point starts moving around and it comes back to the same spot, this arrow will come back to itself. I mean, this is pretty easy to imagine if you see the shape of the cylinder. But then there is this cousin of cylinder, which is called the Möbius band. And this Möbius band, it has this kind of a shape. And this shape can be also obtained by gluing, taking a piece of paper and gluing two sides, but by a twist. And now this Möbius band has this property that if you start with an arrow at this spot here, and you try to do the same thing, and you let this point run around in the middle of this surface, then you come back to the same point, and then this arrow will point in a different direction. So, and that's sort of the qualitative characteristic difference between these two shapes. And this property really distinguishes them. And that's what topology is about. Sort of, you give me two objects, and I find one property, and then I find another property, and these two properties are different for these two surfaces, so I conclude that they are different. And this property in topology is called orientability, for example. This tells you that the cylinder is orientable, whereas Möbius band is not. Okay, so this was just a warm up, to show you what kind of properties we will care about. So now you should fasten your seatbelts because things are gonna get a bit more complicated. No, I'm joking. So now we're gonna start with looking at pretty easy objects. And these objects are beautiful objects, very regular objects called Platonic solids. And so here is the list of Platonic solids: tetrahedron, icosahedron, dodecahedron, octahedron, and cube. And one of the goals of this talk is to show you that these are the only ones in certain sense. And this was already kind of known by Plato in old Greece. All right, so another way of looking at them, if you have never seen these objects, and now I should tell you what these are. So what are the Platonic solids? First of all, they are polyhedra. So a polyhedron is a three-dimensional shape with flat polygonal faces, straight edges, and sharp corners or vertices. Like, if you don't understand this definition, at least look at these pictures, and these are the type of things that are polyhedra. So some kind of shapes with flat faces and edges and corners. And you see that they come in many different types. Like, for example, here we have some of these star-shaped things. But obviously there are many of these, and we want to get Platonic solids out of them. So we need some extra properties what these Platonic solids satisfy in order to be able to distinguish them out of the rest of the world of polyhedra. So the first property what this Platonic solid satisfies is that they are convex. I don't want to really define what convex is officially. Here I will show you something which is not convex. So if you look at this picture, you see this star-shaped surface here, and this is an example of something not convex. And what does this really mean? If you take these two vertices here, for example, if you see, hopefully you can see my mouse. If you try to connect these 2 points with a straight line, then you're going to go outside of this shape. And this means that this thing is not convex. Whereas Platonic solids are, of course, convex, like the pictures you saw. Those were all convex. So we definitely want convex polyhedra. So now topology studies characteristic properties of polyhedra, and it's one of the things it studies. And so let's investigate what are the general properties of convex polyhedra. And so here are the things that always come with a polyhedron. So every polyhedron has edges, faces, and vertices. Like on this picture on the left with the colors, you see this gold, gray, and red. So the gold color, these are the vertices, these gold little points. These gray lines, these are the edges, and the red things, these are the faces. So I will denote by V number of vertices, by E number of edges, and by F number of faces. And now in this case with the tetrahedron pyramid, on the left or on the right. Let's ignore this box for a second. V is equal to 4. As you see, there are these 4 little gold points here, and that's 4. E is equal to 6, and that is exactly these gray edges here, what you see. And F is equal to 4. So like if you look at this picture, there are exactly 4 faces. This standing 3 triangles and the bottom triangle. Okay, but now what these things satisfy is that if you take vertices minus edges plus faces, so number of vertices minus number of edges plus faces, which is V minus E plus F. Let's see what happens in this example. I mean, most of you hopefully remember calculations in the school. 4 minus 6 plus 4 is equal to 2. Everybody can compute that, right? Great. And it turns out that if you do the same thing for this box, which I don't want to write down now, again, this V minus E plus F will be equal to 2. Okay, so is this a coincidence? Let's look at another example, less regular example. For example, such a thing. This is definitely not a regular polyhedron, but it's still pretty good looking polyhedron. So here you have 6 vertices, 9 edges, and 5 faces. Like on the picture, the violet ones are vertices, the red ones are edges, and blue ones are faces. And again, you take V minus E plus F, so vertices minus edges plus faces. This case, it's 6 minus 9 plus 5. So let's do this computation. I mean, everybody can do this again in this audience, I hope. That's equal to 2 again. Wonderful. So what's going on here? So it turns out that this is a general phenomenon, and this is often how mathematics works. You observe examples, and then you guess that something should be true. And this guy called Leonhard Euler in 18th century, very famous Swiss mathematician, one of the greatest mathematicians of all time, here shown on the banknote of 10 Swiss franc. This guy proved that for any convex polyhedron, if you take vertices minus edges plus faces, so V minus E plus F, that is equal to 2, always. And it turns out that this is a consequence of the shape of a convex polyhedron. This is a consequence how these convex polyhedra look like. It's their characteristic property. So it doesn't really matter how big they are, or what are the lengths of these edges, or how big these corners in the vertices are. I mean, what really matters is just the shape of this convex polyhedron, and this is a characteristic property of that shape. So that's what kind of the properties topology is interested in, that like particular shapes satisfy some properties independent of how big they are. And just to mention, what does this have to do with modern maths? I mean, this expression is a special case. This V minus E plus F is a special case of something way more general called Euler characteristic, which is a very important subject of study of modern topology. Let me throw in here some buzzwords. It can be defined in terms of something called homology. And this homology is something that topologists encounter on daily basis. So for example, I don't know, yesterday, maybe I was computing something and I was using, I think, homology, for example. And maybe, oh yeah, yesterday I actually attended a talk which was doing some cool things with Euler characteristic, for example. So, you know, this is very close to modern topology. It's just like it's a very, very special case of something which is more general in research. All right, so that's Euler's theorem. So why do we care about Euler's theorem? So this allows us now to classify Platonic solids. So, but before I tell you this, just to make a point here, I was talking about convex polyhedra. This property, this V minus E plus F equal to 2, fails for non-convex polyhedra, and this is an example. Like this thing here is not convex, but it's a polyhedron. But if you look at this expression, vertices minus edges plus faces, in this case, it's equal to 5 and not to 2. So that equation was really characteristic for convex polyhedra. All right, so now we are ready to define Platonic solids. So give an official definition. A Platonic solid is a convex polyhedron which is regular. So a convex polyhedron is regular if all faces are identical regular polygons, all side lengths are equal, and all angles are equal. So once again, what matters here is that these lengths and angles are equal. It doesn't really matter how long they are or how large they are. So we are just interested in this qualitative property, characteristic property of these lengths and angles, that they are equal. We don't care how long they are or how big they are. So, and here is example. I mean, the claim is there are only 5 Platonic solids, and let me show you how you do this. And here are all of them. And again, Plato was saying that these are all of them, but he couldn't prove it. Now we can prove this. So of course, we're going to use Euler's theorem. We're going to use this equation, which we mentioned here. And let n denote the number of edges of each face. For example, here, this is 3 because we have triangles here. Here, this is 6 because here we have a hexagon. Here it's 4 because we have squares. And m denote the number of edges meeting at every vertex. Like in this case, it's 3. In this case, I think it's 1, 2, 3, 4, 5. In this case, it's 4, 1, 2, 3, 4. And it turns out now that we have these two equations. One is Euler's equation. And on the other hand, we have this equation, which is a consequence of being regular. I don't want to go into like how this equation now follows. But anyway, so we do know that every Platonic solid should satisfy these two equations. And this is how things work. You have something geometric, you translate it into algebra, then you see that these things should satisfy these equations. And then what you conclude, you solve these equations and you conclude that there are only 5 possible solutions for these equations. I mean, I don't want to tell you how you solve exactly these equations. And so here are the solutions, 5 solutions. And because you exactly have 5 solutions, you conclude that these exactly correspond to the 5 Platonic solids. The fact that these equations have 5 solutions exactly tell you that there are only 5 Platonic solids. And this is how often topology works. So you translate the problem into algebra, you solve it into algebra using some equations or identities, and then you go back to geometry and conclude something in geometry, which is typical way of working in topology. All right, so I hope you understood this. Now, why do we care about these Platonic solids and classifying them? I mean, of course, things in nature often have symmetries, and knowing in advance what kind of symmetries you can expect is very useful. I mean, and Platonic solids are these kind of symmetric objects. They, for example, show up in molecular structure of crystals in chemistry engineering, or they also show up as shapes of certain viruses, for example, in microbiology, medicine. And I mean, unfortunately, these days, viruses are pretty important. So let's have a look. I mean, these are some viral shapes. And often these viral shapes have a form of icosahedron or dodecahedron or truncated dodecahedron, depending on what kind of viruses you have. But then again, like some of the other shapes might also show up, like cylinder we already discussed, and then we will soon hopefully discuss also spheres. And these are here the spherical shapes. So just that you know, this talk was advertised 20 minutes, but I surely will go over time and it will be maybe another 2-3 extra minutes. All right, so what about other shapes? As we see, viruses also can be other shapes, so we should also study other shapes. So one of the things also topology studies are knots. Like these are also like these kind of, some knots in dimension 3. And so what topology wants is to distinguish these knots. And studying knots actually probably goes again back to classical era. This is a famous picture of Alexander the Great cutting the Gordian knot. It's a famous story that somebody brought Alexander some knot to untwist, and Alexander couldn't do it, got angry and cut it with a sword. And what knot theory is about is trying to avoid that. So knot theory is a part of topology, which studies knots. And given 2 knots, one is interested if one can get one knot from the other by wiggling or continuously deforming. And cutting and gluing is not allowed. So you are not supposed to cut it and glue it back. You're only interested if you, by continuous procedure, can get one from the other. And so what Alexander did, that was an illegal move. And knot theory is trying to avoid that. Okay, so what are the applications of knot theory before I tell you how exactly knot theory works? It's everyday life. Like you can do this in genetics as well, like something called untangling DNAs. If you have seen models of DNAs, they are kind of knotted type shapes. Then you have quantum computing, which is in computer science an important thing because usual computers sometimes cannot do some very big calculations, and then you need quantum computers. And these quantum computers are based on some kind of schemes which you can build. And this is a typical scheme for quantum computer. And then these shapes look like knots, and then you need to know some knot theory in order to be able to operate with them. Anyway, so we want to distinguish knots. That's what topology is trying. And you see at this picture, for example, if you take this 7,1 and 7,2, then you want to distinguish these two. And how do you know that you cannot deform around that 7,1, for example, and get 7,2? I mean, it's not completely obvious. And so there was another Alexander, now this time in the 20th century, a guy called J.W. Alexander, or James Waddell Alexander II, as opposed to Alexander I the Great. And this guy introduced something called Alexander polynomial. I mean, we call it Alexander polynomial. Of course, he didn't call it like that. And he associated to every of these shapes some formula called Alexander polynomial. So given every knot, you can associate to it some formula, look at the formula, and then conclude something about this knot. And this is how it works. So this Alexander polynomial can distinguish knots. And so for each of these knots, for example, the corresponding formulas look like this. Like for this fivefold knot, it's like this. And what is the point of this formula is that if you look at these, you obviously see that this formula is different from that formula. And the way it works, because you see that these two formulas are different, you can conclude automatically that there is no way to wiggle around, deform this fivefold knot to get a trefoil knot. And that's another example how topology works. We had knot theory, we had knots, we wanted to distinguish them, we translated it into algebra. We see something in the algebra, and now we can conclude something back in topology, in geometry. All right, so now the next thing what I want to mention, and I'm already kind of running out of time, so I will speed up here. So more complicated things, so spheres. So here is an example of what topologists like to study. These are 2 points, and this is a zero-dimensional sphere. This is a circle, and that's a one-dimensional sphere, and this is the usual sphere, which we call a two-dimensional sphere. And why do I mention these? Because in this talk, I want to end this talk by discussing something called three-dimensional sphere, and there are higher dimensional spheres, Sn for NEN, but in this particular case, I'm interested in three-dimensional sphere, which lives in a four-dimensional world. And this is how it looks like. So a three-dimensional sphere is impossible to draw because we live in a three-dimensional world. But mathematicians and physicists, of course, imagine that they live in a four-dimensional world or in any dimensional world. And so this picture here tries to draw three-dimensional sphere in terms of imagining it as a family of circles over a two-dimensional sphere. So this is a two-dimensional sphere, and these points are running over it, and these circles are creating here some kind of twisted shape. And locally, you can sort of see it, but globally not. And in order to better imagine this thing, we should now look at the video. I have it already ready here. And let me know if you cannot see it. So this is the video due to Niles Johnson, actually. I know this guy is a very good topologist and very cool guy. I haven't met him for a while, but he's also very good at making videos. And now, as you see here, this gray thing is a two-dimensional sphere, and the points are running around it. And while the point is running around it, every point here gives you a circle in this picture, the corresponding circle. And while these points are moving around on the sphere, those circles get twisted in each other and creating some funny shape. So let me go a bit farther to make here this thing even more crazy. So like this is how it goes, and then things become even crazier after this point. And let's see that, and then you're gonna see the picture I have drawn. So this is how the three-dimensional sphere is created using circles corresponding to points running on a two-dimensional sphere. All right, so we can now stop this video and go back to the last couple of slides I have left. And I'm already quite over time here, but I just want to finish it in a reasonable way. So this procedure, what you just saw, this is called fibration. So this video, what you saw is a general phenomenon. A presentation of shapes in this form are called fibrations. And these fibrations, this particular example is a Hopf fibration discovered by Heinz Hopf. And just that you don't think that this guy like me is always just drawing pictures and looking at videos. Like this video, what you just saw is this formula. I mean, what we really work with are these type of formulas and not those kind of videos, of course. But that you can ignore if you don't like formulas. And so one of the most serious tasks of modern topology is to study such vibrations and use them to understand geometric objects. Now, this video, what you saw, is a special case of some structure that shows up every day, basically, in a topologist's life. Like, for example, yesterday I was struggling with some vibration, which is probably a more complicated vibration than the one you saw. And okay, now because I'm extremely over time, this is the last slide I have so that you don't get scared. So these vibrations, like these kind of video, what you just saw, these kind of structures are very useful in modern physics, for example, in string theory. Like this is something you saw at the beginning of this talk. This is called Calabi-Yau threefold. And why is this important? This is something six-dimensional. And what you just see here is projection in a three-dimensional space. And it turns out that there is a vibration like this type of video, what you saw, but instead of circles and spheres, now we have this crazy gadget. And we have a four-dimensional space called the Minkowski space, used in general relativity theory of Einstein. So Einstein's theory is four-dimensional. As you know, the fourth dimension is time. And if you take, instead of this two-sphere, the four-dimensional Einstein's relativity theory, and you take, instead of circles, this six-dimensional Calabi-Yau threefolds, and then you have some kind of vibration. So you can make a mix out of these two, and then you can make a 10-dimensional space out of that. And that's the model of one of the models of string theory. So string theories tell us that the world is 10-dimensional, and the world is a mix of Einstein's relativity theory and something six-dimensional, some extra dimensions. And what is this mix? This mix is exactly this vibration, the type of thing what you saw in the video. All right, so I think this is all I wanted to say. Thanks for your attention. And I just want to thank Aberdeen Science Center and India Copeland and Debbie Mothers and also Maha Bishek for organizing this event and setting up all. Also Maths Week Scotland, I would like to thank them for making us aware of these kind of events. And I would like to thank my university and my math department for encouraging me to do this thing. And I'm sorry for going, I think went 5 minutes or something over time. So sorry for that.
Thank you so much, Irakli. Thank you very much. Yes, if we can have a little round of applause on with our reactions, that would be fantastic. Thank you so much. Nobody's left, so you're good with time. You're good with time. Don't worry about that at all.
Maybe they just turned off my sound at some point.
I would like to welcome anyone to ask any questions. You can either pop it in the chat or you can unmute yourself and ask a question. It can be based around what Irakli's been talking about, or maybe he can take a punt at some other maths related questions, but I don't want to promise that from him. So yeah, is any questions at the moment? Maybe while people are thinking of questions, I'll pop one in. How did you end up studying topology?
Oh, that's a good question. So, I mean, I think one of the reasons why I ended up studying topology is that I had this book as a school, in the high school, something called what is mathematics or something like this. I forgot it. This famous guy called Courant who wrote that book. And I remember first time my encounter with topology was to see these pictures in that book. So I got really interested in what these pictures were. But then the reason why I actually ended up with topology is something more abstract. So there is a foundational aspect of this topology called point set topology, so which is not based on pictures. And as a student, I really liked this subject because it was very clean subject somehow. It was describing all these geometric phenomena completely in terms of math without ever doing anything geometric. And so I understood that, like, okay, all these geometric things, they look cool, but there is a way actually to do these in a very clean, formal way.
And I guess, is that the kind of thing where you were saying where you then move into algebra to solve it?
Exactly. So and this is why I ended up doing this kind of thing. Like, you have this very geometric thing and you don't want to really mess around with geometric figures. Instead, you translate it into algebra, and then you do things there, and then you come back somehow and do geometry. And so you actually did much cleaner work in algebraic side than on the geometric side. And that's sort of like why I got interested in this, that like there was a way of actually doing these very difficult geometric things in terms of algebra. That was kind of cool, yeah. So I
Okay.
think that's the main reason how I ended up with this. Yeah.
Yeah, we've got a couple of questions in the chat. So Lindsay's asked, what sort of research do you do? And could it be used for code breaking or encryption?
Oh yeah, so what kind of research? I mean, I do a lot of research in this topology. So like, for example, these vibrations, like, let me go back to this thing, like these type of structures, these vibrations, or like these kind of things. So what we try to do is that, I mean, now this was a simple example. We have sometimes way more complicated objects. We want to understand which motivation for studying these objects, again, could come from physics or many other things. And it turns out that studying these kind of shapes requires some technology, like, for example, these vibrations. And then you want technologies that study these kind of vibrations. And one of the things what I research, for example, is these kind of vibrations, or things that can be used to say something about these kind of vibrations, and also just using these vibrations in other type of problems of topology and so on. So it's studying these kind of geometric objects, but also higher dimensional ones, for example. Like, it doesn't have to be, as I was mentioning, it was a 6-dimension, 10-dimension, and so on. So like, the area which I work in is called Homotopic Theory, and that more studies like studying these kind of objects up to deformations. And I also do a lot of algebra, because a lot of algebra is motivated by these things. And then you have to do a lot of algebra as well. Now, another question, what about encryption kind of stuff, right? The codes and stuff. That is related to knot theory, actually. So let's go back to this quantum computing business. Yeah. So this quantum computing is something that does RSA algorithms that's used in cryptography, for example. So you have some ways of encrypting some kind of things, and there are some big numbers you have to use for this. And this quantum computing, for example, is very useful for that. Yeah. So I hope this answers at least a bit your question. Yeah.
Cool. And I think as well, I remember you saying that your research is very theoretical and not applied. So maybe the stuff that you're doing at the moment won't be used or applied.
Yeah, that is right. I mean, of course, like, actual current research I'm doing is very abstract. But, like, some of these things I was talking about, which are nowadays used, maybe 50 years ago or 100 years ago, was also considered to be very abstract. But then eventually they all got used in technology and these kind of things. So yeah, I mean, mostly the research I'm doing is pure fundamental research, and it probably will be later used, hopefully, some of it. Yeah. I see some more questions.
I was going to say, the other question we've got is, could you give us a quick idea of what homology is?
Yeah. So one of the ideas of homology is that, like, imagine you have a surface or something which has holes in it. So what homology really does is the way to count these holes. Like, for example, you have a torus that has one hole. Homology would see that. And so if you have like some object that has, like, say, 4 holes, and the other object that has 5 holes, then you're gonna sort of capture the difference between these two. Of course, you see that these two things look differently, but what's the mathematical way of distinguishing them? And that's what homology does, sort of seeing these things, that how, like, what's the genus somehow of this surface, for example, is seen by homology. Like, homology is going to distinguish between disk and circle, because disk doesn't have holes in it, whereas circle is just something in a sort of a tube-shaped kind of thing, right? So yeah, that's what homology does, distinguishing.
Sorry, I'm just aware that some people are popping off the call, and just before everybody leaves, I'm just going to launch the poll. Yeah. We'll still keep answering questions, but it would be great if you could just answer the poll, just so we can get a little bit of feedback. And India's also going to pop a feedback link in the chat to get a bit more in-depth feedback, and it would be great if as many people as possible could fill that in, not just for the Science Centre to improve events like this, but also for Irakli to know what you enjoyed and what you'd like to hear more about. So I'm going to keep that open. As I said,
I hope that
stay in and answer some questions.
This answer what I gave, I hope, about homology, that was okay. I hope. I mean, I don't know if you want to study more homology, and I see who is asking this question, you got to attend the algebraic topology class of the 4th year, so.
So the other question we've got is, are there other ways of distinguishing between knots besides Alexander?
Yes, definitely. So Alexander polynomial was the first one that was invented. There are much better ones that can do this. There is so-called Jones. There is so-called Jones polynomial, which is much better way of distinguishing knots. Jones polynomial is even a better invariant, which is the complete invariant somehow, I think. Like 2 knots are equivalent, I think, if and only if their Jones polynomials are equivalent, as far as I remember. Or maybe I'm wrong, but very often it's the better invariant. Yeah, Alexander polynomial cannot always distinguish between knots. Whenever it's different, then it can distinguish, but you might have 2 different knots with the same Alexander polynomial. So a much better one is the Jones polynomial. And I think Jones was awarded actually Fields Medal for inventing that. So, which is the biggest prize you can get in mathematics. So yeah, so there are better ways distinguishing knots than Alexander polynomial. I just have mentioned it because it's probably the only polynomial for knots I know properly. So
thank you. Right. Any other questions at that point? There doesn't seem to be any other in the chat. So I think, Irakli, have you got anything you'd like to say before we sign out?
No, I just want to thank you, everybody, for attending it. And I hope you guys had fun. That's all I can say.
I'm going to stop